Let me tell you something that will absolutely shatter the comfortable little picture you have in your head about the universe. You think you know cold, you think Antarctica is cold, you think your ex's heart is cold? No, no, no. You have absolutely no idea what cold really means. Here's what nobody tells you right now as you're sitting there, breathing, blinking, feeling perfectly warm and comfortable. There are places in this universe so devastatingly, so incomprehensibly cold that every single atom has essentially stopped moving, stopped, dead. Like someone hit a cosmic pause button on reality itself. The coldest place we've ever found in all of nature isn't where you think it is. It's not at the bottom of some frozen ocean. It's not buried beneath miles of Antarctic ice. It's up there, in space, hanging silently in the dark. And when I tell you exactly how cold we're talking and what's happening at that temperature at the quantum level, I promise you, your brain is going to do something very uncomfortable. It's going to question everything. You know what's funny about human beings? We experience something our entire lives, something as basic and fundamental as temperature, and we still manage to completely misunderstand what it actually is. Cold. We all know cold. We've all felt it. We pull on a jacket. We blow warm breath on our frozen fingers. We say things like, "It's cold outside," as if we understand exactly what we're describing. But here's the thing, and this is something that genuinely delighted me when I first learned it as a young physicist. Cold doesn't actually exist as a thing. That's right. Cold is not a substance. Cold is not a force. Cold is not something the universe produces. Cold is simply the absence of heat. And heat now, this is something real, something physical, something we can actually grab onto with mathematics and hold up to the light and examine. Heat is molecular motion, pure and simple. When something is hot, its atoms and molecules are moving. They're vibrating, rotating, bouncing around like little maniacs at a party that never ends. When something is cold, those same atoms are moving less. They've slowed down. The party's dying. The music's getting quieter. And this simple, beautiful, elegant idea leads us to one of the most profound concepts in all of physics. If cold is just the absence of molecular motion, then what happens when all motion stops completely? The thermometer's dirty little secret. Now, let me back up for a second, because I want to make sure we're all on the same page here. Most of you grew up with thermometers. Fahrenheit, Celsius, take your pick. These scales are perfectly fine for everyday life. You want to know if you should wear a coat? Celsius will do the job. You want to cook a turkey? Fahrenheit's got you covered. But these scales have a dirty little secret that most people never think about. They're arbitrary. Celsius is based on water. 0 is where water freezes. 100 is where it boils. That's it. That's the whole story. There's nothing fundamentally special about water from the universe's perspective. The universe doesn't care about water. The universe doesn't care about you, for that matter, but that's a philosophical conversation for another day. Fahrenheit, even more arbitrary. Daniel Fahrenheit calibrated his thermometer using a mixture of ice, water, and ammonium chloride. The number 32 for the freezing point of water, completely made up, historically convenient, scientifically meaningless. So here's the question that changed everything. Is there a temperature scale that's not arbitrary? Is there a scale that's grounded in something real, something the universe itself would recognize? The answer is yes, and its name is Kelvin. William Thomson and the absolute scale. In the mid-1800s, a brilliant Scottish-Irish physicist named William Thomson, who you might know better by his title, Lord Kelvin, was wrestling with exactly this problem. He was studying the behavior of gases, and he noticed something extraordinary. When you cool a gas, it contracts. Makes sense, the molecules slow down, they don't push outward as hard, the gas takes up less volume. Simple enough. But Thomson started doing the math, and he found something astonishing. If you extended the graph, if you kept cooling and cooling, mathematically speaking, all gases would reach 0 volume at exactly the same temperature, minus 273.15 degrees Celsius. Every gas, every time, without exception. Now, obviously, real gases don't actually reach 0 volume. They turn into liquids and solids before that happens. But the mathematics was pointing to something profound. There is a temperature, a specific, universal, absolute temperature below which nothing can go, a floor, a hard limit, a wall that the laws of physics themselves have built. This temperature became known as absolute zero. And on the Kelvin scale, it's simply called zero. 0 Kelvin, 0 K. Nothing below it, nothing. Not a single fraction of a degree. What actually happens at absolute zero? Now here's where it gets really interesting. And I mean really interesting, the kind of interesting where you're lying in bed at night unable to sleep because your brain won't stop chewing on it. At absolute zero, molecular motion stops. The atoms freeze in place. The thermal energy, the kinetic energy of random motion drops to zero. In classical physics, this is perfectly straightforward. Cold enough means still enough. Simple. But then quantum mechanics walks into the room, sits down uninvited, and completely ruins the neat, tidy classical picture. Here's what quantum mechanics tells us. You can never actually reach absolute zero. Not because of any engineering limitation, not because our refrigerators aren't good enough, but because of something called the Heisenberg Uncertainty Principle. The uncertainty principle, and I find it endlessly amusing that people think this is just a technicality, a minor footnote, states that you cannot know both the position and the momentum of a particle with perfect precision simultaneously. The more precisely you know where something is, the less precisely you can know how fast it's moving, and vice versa. Now think about what absolute zero would require. It would require every atom to have exactly zero momentum to be completely, perfectly still. But if we know the momentum is exactly zero, then by the uncertainty principle, the position becomes completely undefined. The atom could be anywhere. And that's not what frozen in place means. So nature has this beautiful, frustrating, wonderful built-in safeguard. Even at the coldest possible temperatures, atoms retain what physicists call zero-point energy, a tiny, irreducible quantum jiggle. They're never completely still. They can't be. The universe won't allow it. Absolute zero is not a destination. It's an asymptote. You can approach it. You can get extraordinarily close. But you can never, ever arrive. How close have we gotten? Now, the next obvious question, and it's a good one, the kind of question a genuinely curious person asks is, how close have we actually gotten? And the answer is stupidly, almost impossibly close. In laboratories, using techniques I'm going to describe in detail later in this script, physicists have cooled matter to temperatures of 100 picokelvins. That's 0.00000000001 Kelvin. 1/10 billionth of a degree above absolute zero. Let me put that in perspective for you. The surface of the sun is about 5,778 Kelvin. The room you're sitting in right now is roughly 293 Kelvin. The coldest natural temperature we've recorded on Earth in Antarctica is about 184 Kelvin, minus 89 degrees Celsius. And in these laboratories, scientists are achieving temperatures that are not just colder than anything on Earth. They are colder than anything in the known natural universe. Which brings us to the central mystery of this whole conversation. What is the coldest natural place? If laboratories can achieve temperatures colder than anything nature produces, then what is the coldest natural place? Where, without any human assistance, without any cooling equipment, without any laboratory tricks, does nature get coldest? You might be tempted to say deep space. The background temperature of space, the temperature of the cosmic microwave background radiation, the afterglow of the Big Bang is about 2.7 Kelvin. That's minus 270.45 degrees Celsius. Extraordinarily cold, almost incomprehensibly cold. But that's the average, the baseline. The cosmic background hum. There are places in space that are colder, dramatically colder. Places where nature, through processes both violent and serene, has managed to push temperatures down to levels that make the background of space look positively balmy. And the winner, the undisputed champion of cosmic cold, the coldest naturally occurring place we have ever discovered in the universe is a nebula, a specific, remarkable, almost eerily beautiful nebula sitting about 5,000 light years away from Earth. The deeper question, but before we travel 5,000 light years to visit the universe's natural freezer, I want to plant a seed in your mind, a question that I want you to carry with you through everything that follows. Why does cold matter? Not practically, not in terms of ice cream or winter coats. I mean fundamentally, cosmically. Why should a physicist, why should you care deeply about the coldest places in the universe? Here's my answer, and I want you to think about this carefully. The study of extreme cold is, in a very real sense, the study of what holds reality together. When we strip away thermal energy, when we quiet the constant rattling noise of heat, we begin to see the underlying quantum structure of matter with extraordinary clarity. The phenomena that emerge at ultra-low temperatures, superconductivity, superfluidity, Bose-Einstein condensation. These are not laboratory curiosity. They are windows into the fundamental nature of reality. The universe, at its coldest, shows us its most honest face. And as we push toward absolute zero, as we chase that unreachable temperature in our laboratories, while simultaneously finding it in the wilderness of space, we are doing something that has always driven the best science, the most important science, the only science worth doing. We are asking, what is this place? What are the rules? And how far do those rules go? My father taught me something when I was very young. He taught me to look at the world and ask not just what something is, but why it is, and how it connects to everything else. It's a habit I've never been able to break. And I think if you're honest with yourself, you'll find you have the same habit, because you're watching this. And that tells me something about you. It tells me you're the kind of person who needs to know. So let's go find out. 5,000 light years. That's the distance between you sitting wherever you are right now, impossibly small, on an impossibly small planet, and the most extraordinary cold spot in the known universe. 5,000 light years. 30 quadrillion miles, a distance so vast that the light leaving that nebula right now won't reach Earth until roughly the year 7024. Your descendants, if humanity is still around, if we haven't managed to do something spectacularly stupid in the meantime, will be the ones who see the nebula as it looks today. You're seeing it as it looked 5,000 years ago. And even then, even across that incomprehensible distance, even filtered through 5,000 years of cosmic travel, the data we're getting back from that nebula is enough to tell us something that should make your jaw drop. It is 1 Kelvin, 1 single Kelvin, colder than the cosmic background radiation, colder than anything else nature has produced anywhere in the observable universe. The Boomerang Nebula is, without question, the coldest natural place that has ever been discovered. And the story of why it's so cold, that's where things get genuinely spectacular. What is a nebula, anyway? Before I explain the Boomerang Nebula specifically, let me make sure we're all working from the same foundation, because I've noticed that people use the word nebula a lot without really knowing what they're talking about. And I have a profound intolerance for talking about things without actually understanding them. A nebula, from the Latin word for cloud, is essentially a giant cloud of gas and dust in space. They come in different types, different sizes, different temperatures, different origins. Some nebulae are stellar nurseries, places where gravity is slowly pulling gas together until it ignites into new stars. Others are the remnants of dead stars, the material blown outward when a star dies. The Boomerang Nebula belongs to this second category. It's what's called a protoplanetary nebula, the material expelled by a star in the late stages of its life, before it fully collapses into a white dwarf. Now, here's the key physics. When this star expelled its outer layers, it didn't do so gently. It didn't slowly exhale like a tired old man sitting down in a comfortable chair. It blasted material outward at extraordinary speed, roughly 164 kilometers per second. That's about 590,000 kilometers per hour. Fast enough to travel from Earth to the Moon in about 2 seconds. The physics of cosmic cooling and this violent, rapid expansion is the key to understanding why the Boomerang Nebula is so cold. You've experienced this principle in everyday life, even if you've never thought about it this way. When gas expands rapidly, it cools dramatically. You've felt this when you spray aerosol from a can, the can gets cold. You've felt it when air escapes from a bicycle tire valve. You've felt it in the wind chill of a fast-moving breeze. This is called adiabatic cooling, and in the Boomerang Nebula, it's happening on an astronomical scale. The gas being ejected from this dying star is expanding so rapidly across such an enormous volume that it's losing its thermal energy at a rate that drops its temperature below 1 Kelvin. The gas is essentially doing to itself what our best laboratory refrigerators do to carefully controlled samples, except it's doing it naturally, spontaneously, across a region of space about 1 light year in diameter. Nature found a way to build a refrigerator the size of a solar system. And I find that beautiful. I mean that sincerely. When you understand the physics, when you see how the expansion of a dying star's atmosphere translates directly into temperatures colder than the cosmic background, there's a kind of elegance to it that makes you want to just sit quietly for a moment and appreciate the fact that the universe is this well constructed. The discovery story, the Boomerang Nebula, was first observed in 1980 by astronomers Keith Taylor and Mike Scarrett, who gave it its name because of its asymmetric shape it looked through their ground-based telescope like a boomerang. But its extraordinary coldness wasn't confirmed until 1995, when astronomers Raghvendra Sahai and Lars Åke Nyman used the Swedish ESO submillimeter telescope in Chile to study it in detail. What they found shocked them. The nebula was absorbing the cosmic microwave background radiation rather than emitting it. Now let me explain why that's significant. The cosmic microwave background, the 2.7 Kelvin afterglow of the Big Bang that fills the entire universe, should be the coldest thing in the universe, right? Everything should be warmer than it. So everything should be emitting radiation relative to the background. But the Boomerang Nebula was doing the opposite. It was absorbing the background radiation, which means it is colder than the background, colder than the universe's base temperature. Sahai later described this as finding something that should not exist according to our understanding. That's a phrase that should make any physicist's eyes light up like a Christmas tree. Because when something shouldn't exist and then turns out to exist, you've found something worth chasing. Quantum weirdness begins. Now, let's talk about what happens to matter, not to nebulae, but to matter, to atoms, to quantum particles, when you push temperatures down to these extraordinary extremes. Because this is where physics stops being just interesting and starts being actively mind-bending. At normal temperatures, the temperatures of everyday life atoms behave like classical objects. They have specific positions. They have specific velocities. They bounce around and interact in ways that, while technically quantum mechanical at the deepest level, can be very well approximated by classical physics. The quantum effects are there, but they're averaged out, smeared out by the constant thermal motion. The noise drowns out the signal. But when you cool matter down, when you take away that thermal noise, something remarkable happens. The quantum nature of matter becomes visible. Wave-particle duality goes macro. Every particle, every electron, every atom, every molecule has a quantum property called the de Broglie wavelength. This is the wavelength associated with the particle's quantum wave function. And here's the critical detail. This wavelength is inversely proportional to the particle's momentum. At high temperatures, particles are moving fast, they have large momenta, and their de Broglie wavelengths are tiny, smaller than the distances between atoms. The particles behave like classical billiard balls, essentially, because their quantum waves are too small to see each other. But as you cool things down, as you slow those particles, reduce their momentum, their de Broglie wavelengths grow. They expand. They start overlapping with neighboring atoms' wavelengths. And when quantum waves overlap, things get weird. This isn't metaphorical weirdness. This is literal, measurable, reproducible, experimentally verified weirdness. The kind of weirdness that makes very serious, normally calm physicists get genuinely excited and start talking too fast. Superfluidity liquid that climbs walls. One of the first examples of this quantum weirdness emerging at low temperatures was discovered with helium-4. Helium, as most of you probably know, has the lowest boiling point of any element. It remains liquid at temperatures as low as 4.2 Kelvin under normal atmospheric pressure. But cool liquid helium, further to about 2.17 Kelvin, a point called the lambda point, and something extraordinary happens. The liquid becomes a superfluid. A superfluid has zero viscosity. Zero. None. The liquid flows without any resistance whatsoever. It can flow through microscopic holes that regular liquids can't pass through. It can spontaneously climb up the walls of its container, creep over the rim, and flow down the outside, driven by quantum effects alone. I remember reading about the first observations of this phenomenon and thinking, if you showed this to someone without any physics education, they would be absolutely convinced they were watching magic. Liquid flowing uphill, passing through solid walls, moving in ways that seem to laugh in the face of common sense. But it's not magic. It's quantum mechanics. It's what happens when you take away the thermal noise and let the underlying quantum nature of matter express itself without interference. Superconductivity, electricity without resistance. Another spectacular example, and one with enormous practical implications, is superconductivity. At normal temperatures, when electric current flows through a conductor or wire, for instance, the electrons carrying that current constantly collide with the atoms of the material. These collisions produce resistance, and resistance produces heat. This is why your phone charger gets warm. This is why power lines lose energy over long distances. This is a fundamental, unavoidable consequence of the thermal motion of atoms. But cool certain materials below a critical temperature, and this temperature varies by material, but it's always very, very cold, and electrical resistance drops to exactly zero. Not approximately zero, Not very nearly zero. Exactly, completely, perfectly. Electrons pair up into what are called Cooper pairs, quantum mechanical partners that move through the material in a correlated, coherent way. They no longer scatter off the atoms. They flow like a superfluid of charge. A current set in motion in a superconducting ring will continue flowing forever without any driving voltage, without any energy input, without any measurable decay. We've actually done this experiment. We've set up a current in a superconducting loop and watched it for years without any measurable change. Persistent current, eternal, quantum mechanical, and real. The deeper meaning. Now, I want to pause here and make a philosophical observation because I think it's important. Everything we've discussed, superfluidity, superconductivity, the bizarre behavior of matter at low temperatures, all of it emerges from a single fundamental principle. Quantum mechanics is the true description of reality, and heat is what normally hides it from us. We live our lives in a warm, noisy, classical world. Our brains evolved in that world. Our intuitions are calibrated to that world. And so quantum mechanics feels strange and counterintuitive because we've never directly experienced it. But the universe doesn't share our intuitions. The universe doesn't care what feels normal to a collection of biochemical machines on a pale blue dot. The universe runs on quantum mechanics at every scale, at every temperature. It's just that at the temperatures we normally encounter, the quantum effects are hidden, like a radio signal buried in static. Cold is what tunes out the static. Cold is what lets us hear the signal. Thousands of atoms, behaving as one, indistinguishable, united by quantum mechanics in a way that Einstein himself called spooky, and yet completely, undeniably real. In 1924, a young Indian physicist named Satyendra Nath Bose sent a paper to Albert Einstein. The paper was about the statistical behavior of photons, particles of light, and it proposed a new way of counting quantum particles that was fundamentally different from classical statistics. Most journals had rejected the paper. Bose, undeterred, sent it directly to Einstein, because if you're going to be bold, you might as well be completely bold. Einstein read it. And Einstein, who was not in the habit of being easily impressed, was impressed. He translated the paper into German himself and arranged for its publication. Then he extended Bose's ideas to atoms, to actual material particles with mass, and made a prediction that seemed, at the time, almost certainly wrong. He predicted that if you cooled certain types of atoms to temperatures close enough to absolute zero, something unprecedented would happen. The atoms wouldn't just slow down. They wouldn't just freeze in place. They would do something far stranger. They would all collapse into the exact same quantum state. They would lose their individual identities. Thousands, millions of separate atoms would become, in a very real quantum mechanical sense, a single object, not a collection of atoms behaving similarly. One quantum entity described by a single wave function spread across a macroscopic volume. Einstein made this prediction in 1925. We didn't achieve it in the laboratory until 1995, 70 years. That's how far ahead of its time this idea was. That's how extraordinary the experimental challenge was. And when it finally happened, the physicist involved won the Nobel Prize. What is a Bose-Einstein condensate? Let me describe what a Bose-Einstein condensate, or BEC, actually is, because I think the textbook descriptions undersell the weirdness rather significantly. We've talked about how, at low temperatures, atoms' de Broglie wavelengths grow. The quantum waves associated with each atom expand as the atoms slow down. Now imagine you're cooling a gas of atoms, specifically atoms that belong to a class called bosons, particles with integer quantum spin, which follow the statistical rules that Bose first described. As you cool these atoms, their wavelengths grow and grow. And then, at a critical temperature, the wavelengths of neighboring atoms become large enough that they start to overlap. And when boson wave functions overlap, they don't just add together, they synchronize, they phase lock. They become coherent, like laser light, all oscillating in perfect unison. At this point, the distinction between individual atoms essentially vanishes. You no longer have atom A and atom B and atom C. You have a single quantum entity that we call the Bose-Einstein condensate. This is not an approximation. This is not a metaphor. The atoms have genuinely, measurably, verifiably lost They're individual quantum identities. If you try to answer the question, where is atom number 47, the honest answer is the question doesn't make sense anymore. The atoms are indistinguishable. Not because we can't tell them apart practically, but because the universe itself has stopped treating them as separate things. The Cornell-Wieman-Kettle experiment. In 1995, Eric Cornell and Carl Wieman at Gila in Colorado, and independently Wolfgang Ketterle at MIT, created the first Bose-Einstein condensates in the laboratory. The technique they used, laser cooling combined with evaporative cooling, is a beautiful example of clever physics. Here's how it works, in the rough terms that I find most illuminating. Laser cooling uses the momentum of photons, light particles, to slow atoms down. You shine carefully tuned laser beams at a cloud of atoms from all directions. When an atom moves toward a laser beam, the Doppler effect means it sees slightly higher frequency light. This makes it more likely to absorb a photon. And when it absorbs a photon, the photon's momentum kicks the atom backwards, slowing it down. Through this technique, you can cool a gas of atoms to a few millionths of a Kelvin, which is extraordinary. But it's not cold enough for BEC. So then you use evaporative cooling. The same principle as a hot cup of coffee cooling down, the most energetic molecules escape, carrying their energy with them, leaving the remaining molecules cooler on average. By carefully tuning the conditions so that only the fastest, hottest atoms escape the trap, you can drive the remaining gas down to temperatures of a few hundred nanokelvin. And at those temperatures, temperatures colder than anything in natural space, the Bose-Einstein condensate forms. Cornell, Wieman, and Ketterle didn't just create something cold, they created a new state of matter. Not solid, not liquid, not gas, not plasma. Something new, something that had existed only in the mathematics of quantum mechanics for 70 years suddenly materialized in a laboratory in Colorado. The universe is cooling down. Now let's zoom out, way out. Let's talk about the biggest picture possible. Because here's a fact that I think deserves far more attention than it gets. The universe has been cooling down since the moment it was born, and it will continue cooling forever. At the moment of the Big Bang, in the first fractions of the first second, the universe was incomprehensibly hot. Temperatures of 10, 32 Kelvin. Numbers so large they're essentially meaningless to human intuition. At those temperatures, the fundamental forces of nature were unified. There was no distinction between gravity and electromagnetism and the nuclear forces. It was all one thing, at one temperature, in one state. Then the universe expanded. And as it expanded, it cooled. The way our nebula cools, on an infinite scale, at about 10, negative 12 seconds after the Big Bang, temperatures had dropped to around 10, 15 Kelvin, and the forces began to separate. At about 1 second, the temperature was around 10 Kelvin, hot enough that the universe was a dense plasma of protons, neutrons, and electrons. At about 380,000 years, the universe had cooled to roughly 3,000 Kelvin, cool enough for electrons to combine with protons and form neutral hydrogen atoms. The universe became transparent for the first time. Light could travel freely. The cosmic microwave background is the snapshot of this moment, stretched and cooled by expansion to its current 2.7 Kelvin. And 13.8 billion years later, here we are, at 2.7 Kelvin on average, with some hot spots, stars, and galaxies, with some cold spots, nebulae like the Boomerang. But the trajectory is clear. The universe is cooling, inexorably, asymptotically approaching the temperature that physicists have given the haunting name of the heat death. The heat death of the universe. The heat death, or the big freeze, is one of the predicted ultimate fates of our universe. And it is, depending on your temperament, either the most depressing or the most awe-inspiring concept in all of cosmology. Here's the basic idea. The second law of thermodynamics tells us that entropy disorder always increases in a closed system. The universe is, as far as we can tell, a closed system, so its entropy is increasing, always, without exception. As stars burn, they convert organized, structured energy, nuclear fuel, into heat, which disperses into the void. As time goes on, more and more of the universe's energy becomes unavailable, spread too thinly, too uniformly to do useful work. Eventually, in timescales that make the current age of the universe look like the first millisecond of a billion-year story, the last stars will burn out. The last black holes will evaporate via Hawking radiation. The protons themselves may decay. And the universe will settle into a state of maximum entropy, cold, dark, uniform, still, a temperature approaching absolute zero, everywhere, forever. No gradients, no energy flows, no complexity, no life, no thought, no physics worth doing, just a cold, dark, featureless void, expanding forever into nothing at a temperature indistinguishable from absolute zero. Now, is this depressing? Some people find it so. I don't. I find it clarifying. We live in a universe that had a beginning, that is evolving, that is cooling, that has a direction, and the direction is toward increasing entropy, toward a cold death. But right now, in this incomprehensibly tiny window of cosmic time, there are stars, and planets, and people, and thoughts, and curiosity, and physics. There is the Boomerang Nebula sitting cold in space. There is a laboratory in Colorado where atoms have been coaxed into a new state of matter. The universe is dying. Slowly, majestically, on time scales we can barely conceive. And in the meantime, it is extraordinarily interesting. Humanity's race to absolute zero. So against this backdrop, a cooling universe, a theoretical floor we can never quite reach, what have human beings been doing? Racing toward that floor, relentlessly, with characteristic ingenuity and stubbornness. The history of low-temperature physics is, in a very real sense, the history of human beings picking a target that the laws of nature say is unreachable and then getting as close to it as physics allows. It started with the liquefaction of gases. In the 1800s, gases that had seemed permanent, that had resisted all attempts at liquefaction, began to fall one by one. Oxygen, nitrogen, hydrogen. Each one required colder temperatures than the last. Each one required new techniques, new equipment, new cleverness. The final holdout was helium, the lightest noble gas with the lowest boiling point of any substance. It wasn't liquefied until 1908, when the Dutch physicist Heike Kamerlingh Onnes, working in his laboratory in Leiden, the Netherlands, managed it for the first time. Onnes reached a temperature of 1.5 Kelvin. At the time, it was the coldest temperature ever achieved by humanity. He won the Nobel Prize in Physics in 1913. And in his laboratory with liquid helium, he made the first observations of superconductivity, discovering that Mercury's electrical resistance dropped to exactly zero at 4.2 Kelvin. That was the beginning. And in the century since, we have not stopped. Modern cooling techniques. Today, the techniques we use to reach ultra-low temperatures are extraordinary pieces of both physics and engineering. Dilution refrigerators, devices that exploit the quantum mechanical properties of helium-3 and helium-4 mixtures, can reach temperatures as low as 2 millikelvin, 2/1000ths of a Kelvin above absolute zero. Laser cooling, as I described earlier, can reach the microkelvin range. Evaporative cooling pushes further into the nanokelvin range. And at the absolute frontier, using a technique called adiabatic nuclear demagnetization, which exploits the quantum spin states of atomic nuclei, laboratories have achieved temperatures of 100 picokelvins, 100 trillionths of a Kelvin above absolute zero. To put that in perspective, the ratio between room temperature and 100 picokelvins is roughly the same as the ratio between the size of the observable universe and the size of a single proton. We have pushed into temperature territory that no natural process in the universe has reached. In the basements of physics laboratories, in carefully shielded chambers, we have created conditions colder than the Boomerang Nebula, colder than the cosmic microwave background. The coldest spots in the known universe are inside human-built machines. That thought genuinely thrills me. It always has. Not because it makes us special. The universe is vastly larger and more complex and more ancient than we are, and we should remain humble about that. But because it demonstrates something important about the enterprise of science. The laws of nature set limits. Human ingenuity finds out exactly where those limits are. We haven't reached absolute zero. We never will. The uncertainty principle guarantees it. But we have traced the asymptote down so close, so incredibly close, that we have been able to observe quantum phenomena that have transformed our understanding of matter itself. Let me tell you about the time I burned myself with cold. It was during my early years of playing with low-temperature physics, and I was handling liquid nitrogen, which at 77 Kelvin is about the temperature of a shy little amateur compared to what we've been discussing today, but still more than capable of making a point quite forcefully. I was moving quickly, the way young physicists tend to move, because we're always excited and always in a hurry, and a small amount of liquid nitrogen splashed onto my hand. And here's what's fascinating about it. It didn't burn me immediately. Because of something called the Leidenfrost effect, the liquid nitrogen instantly vaporized at the skin surface, creating a thin insulating layer of nitrogen gas. I felt intense cold, certainly, but the damage was minimal. Now, had I been in sustained contact, had I plunged my hand into liquid nitrogen and held it there, the story would be very different. The tissues would freeze. The water in the cells would form ice crystals, destroying cellular structure. The damage would be severe and irreversible. But we're not talking about liquid nitrogen today. We're talking about temperatures 1 billion times colder than liquid nitrogen. So let's ask the real question. What would happen if you touched a Bose-Einstein condensate? What would happen if you somehow made contact with the coldest thing in the universe? The physics of extreme cold contact. First, let's be clear about the practical reality. A Bose-Einstein condensate existing at temperatures of hundreds of nanokelvin is an extraordinarily delicate thing. It typically contains on the order of millions of atoms held in a magnetic or optical trap. The entire condensate might be a few millimeters across. The slightest vibration, the slightest thermal input from the surrounding environment destroys it instantly. If you somehow brought your warm 310 Kelvin biological hand anywhere near a beck, the radiated heat would obliterate the condensate long before you made physical contact. You wouldn't touch it. You would end it. But let's do what physicists love to do. Let's run a thought experiment. Let's imagine purely hypothetically that we have a piece of matter at 100 picokelvins. Not a delicate quantum gas, but a solid object, somehow maintained at that temperature. And you touch it. What happens? The short answer, the heat transfer would be so rapid and so violent that touching might not be the right word. The thermal gradient between your body 310 Kelvin and the object 0.00000000001 Kelvin would be essentially the maximum thermal gradient possible in the natural universe. Heat would flow from you to the object at an extraordinary rate. Your skin would cool catastrophically, instantly. Cells would die. The water in your fingertip would freeze solid before you could even register the sensation. But here's the fascinating physics. The object itself would absorb this heat. Its temperature would rise enormously by its standards, while your skin temperature would plummet. The thermal equilibration would be rapid and violent. In a very real sense, touching the coldest possible thing would be just as dangerous as touching the hottest possible thing. Thermal extremes are dangerous in both directions. The biology doesn't care which way the heat flows. It just cares that the gradient is catastrophic. Cold and biology, the strange relationship. Now, there's a peculiar relationship between cold and life that I find fascinating from a physics perspective. Life, all of it, every form we know, operates within an extraordinarily narrow temperature range. Liquid water is essential, which means temperatures between 273 Kelvin and about 395 Kelvin for the most extreme tolerant organisms. A range of barely 120 degrees on a scale that spans nearly 100 billion degrees of temperature history in the universe. We're thermal creatures. We generate heat metabolically. We regulate our temperature obsessively. Our proteins fold correctly only at specific temperatures. Too hot, and they denature, unfold, lose their shape, lose their function. Too cold and biochemical reactions slow to the point where metabolism becomes impossible. When cells freeze, the ice crystals that form inside them are literally sharp. They puncture membranes. They destroy the intricate machinery of the cell. And yet here's where it gets interesting. Certain organisms have evolved extraordinary adaptations to extreme cold. The tardigrade, that microscopic eight-legged wonder, can enter a state called cryptobiosis at extreme cold, essentially pausing all metabolic activity, expelling water from its cells to prevent ice crystal formation and surviving temperatures close to absolute zero. There are bacterial spores in Antarctic ice that have remained viable for hundreds of thousands of years, frozen, dormant, waiting. There is something profound about this, about life's relationship with cold. Cold slows time in a biological sense. It reduces the rate of chemical reactions, including the chemical reactions that constitute aging and decay. Cold is, in a very real sense, a form of biological pause. The coldest spot we've made, the cold atom lab in space. Here's something that I think perfectly encapsulates where we are right now in this remarkable journey of cold physics. In 2018, NASA launched the Cold Atom Laboratory to the International Space Station. It's a research facility, roughly the size of an ice chest, designed to create and study Bose-Einstein condensates in microgravity. Why space? Because on Earth, gravity limits how long you can observe a condensate in free fall. It falls out of the trap. In microgravity, you can study the condensate for much longer. And in 2020, this facility successfully created the coldest known spot in the universe, not just colder than the Boomerang Nebula, not just colder than the cosmic microwave background, but colder than anything ever recorded anywhere. Temperatures approaching 100 picokelvins in orbit, in a machine the size of a refrigerator, built by human beings. Think about what this means. We have launched a device into space that creates, on demand, conditions colder than anything the universe has naturally produced in 13.8 billion years of existence. We have, in a very meaningful sense, outdone nature in its own extreme. I find this humbling and exhilarating in equal measure. Humbling because it reminds us how capable human curiosity and ingenuity can be. Exhilarating because the science being done in that small laboratory in orbit studying quantum fluids and microgravity will have implications we can't yet fully anticipate. The final question, will the universe freeze? And now we arrive at the question that I've been building toward this entire time. The question that sits at the intersection of thermodynamics, cosmology, and something very close to philosophy. Will the universe freeze? Will this cosmos, which was born in an explosion of unimaginable heat, which has been cooling for 13.8 billion years, which contains within it spots colder than anything its physics should naturally permit, will it ultimately reach a state of zero temperature? A cosmic absolute zero? The honest answer is almost, but not quite. Here's what our best current understanding of cosmology tells us. The universe is expanding. Not just expanding, accelerating in its expansion, driven by what we call dark energy. As space expands, the cosmic microwave background radiation stretches. Its temperature drops. In billions of years, it will drop further and further below its current 2.7 Kelvin. Stars will die. The last star, a dim red dwarf, burning hydrogen slowly, carefully, will exhaust its fuel in roughly 10-14 years, 100 trillion years from now. After that, the universe will be dark, cold, filled with stellar remnants, white dwarfs, neutron stars, black holes, all slowly radiating away their remaining thermal energy into the void. The white dwarfs will cool to black dwarfs, cold, dark, crystalline spheres of carbon and oxygen, relics of dead suns. This will take approximately 10-15 years, a quadrillion years. Then the black holes. Black holes evaporate via Hawking radiation, a quantum process, whereby the black hole slowly radiates energy as virtual particles become real at the event horizon. For a stellar mass black hole, this takes approximately 1067 years. For the supermassive black holes at the centers of galaxies, millions to billions of solar masses, it takes perhaps 100 years. After that, after every black hole is evaporated, after every particle of ordinary matter has potentially decayed, the universe will be cold, extraordinarily, almost incomprehensibly cold. The temperature will be so close to absolute zero that for all practical purposes, it will be absolute zero. The thermal energy remaining will be equivalent to perhaps 1 photon per observable universe. But not exactly zero, because remember, the uncertainty principle will still apply. Space itself will still have quantum fluctuations. Even in the ultimate dark era, even in the maximum entropy state, there will be quantum foam, virtual particles flickering in and out of existence, the irreducible quantum noise that the universe insists on maintaining. The universe will approach absolute zero asymptotically, forever, and never quite reach it. Just like us. What does it all mean? I want to close this conversation, this long, winding, beautiful conversation about the coldest places in nature, with something that I've been thinking about for a long time. There's a temptation, when you learn about the heat death, when you learn that the universe is ultimately heading toward a cold, dark, featureless eternity, to feel a kind of despair, a meaninglessness. Why bother understanding anything if it all ends in cold, dark, nothing? I felt that pull. I think every honest person who thinks seriously about these things has felt it. But here's what I keep coming back to. Here's what I think is the right response to the heat death of the universe. It's happening so slowly And in the meantime, there is so much to understand. The universe had to cool for 13.8 billion years to produce conditions under which hydrogen and helium could organize themselves into stars. And stars could forge heavy elements, and those elements could form planets. And on one particular planet, around one particular star, in one particular corner of one particular galaxy, those elements could organize themselves into something that asks questions. Something that sits in a laboratory and cools atoms to 100 picokelvins and watches them become a single quantum entity and says, isn't that extraordinary? Something that points a telescope at a nebula 5,000 light years away and measures its temperature and says that's colder than the background of the universe itself. I need to understand why. The universe produced curiosity. It produced the desire to understand. And that desire, that specific, peculiar human drive to look at the coldest place in nature and want to know exactly why it's cold and what's happening there and what it means, that is, to my mind, one of the most remarkable things the universe has ever done. Carl Sagan used to say that we are a way for the cosmos to know itself. I believe that. The universe cools, and as it cools, it briefly, for a few billion years here and there, becomes complex enough to understand its own cooling. We are not separate from the universe. We are made of it. The atoms in your body were forged in stellar cores. The water in your cells was synthesized in interstellar space. And the curiosity in your mind, the thing that made you watch this entire video about cold, that is the universe looking at itself and finding itself interesting, and that more than the Boomerang Nebula, more than Bose-Einstein condensates, more than absolute zero, is the most remarkable thing in all of physics. The universe is cold, getting colder, heading slowly and inevitably toward a frozen eternity. And right now, in this moment, it knows it is, because you know it is.